Hello, welcome to your lecture video for Wednesday. Um, so to start out, in physics, we use International Standard or SI units. Time is measured in seconds, length in meters, mass in kilograms. And the rest of these we probably won't use this quarter. Um, and when we're working on physics problems, our units should specifically break down into things like seconds, meters, and kilograms. Also want to point out the symbols or kind of like labels we use for these. So seconds is just S, meters is N, and then kilograms are kg. Next up, let's talk significant figures. When the length of something is listed at 3 meters, it is reasonable to assume that the true length falls somewhere between 2 and 4 meters. If instead the length was given as 3.154 meters, we can assume that the true value falls between 3.153 and 3.155 meters. But if we know the length is 3.154 meters, but we list it as 3 meters, we're withholding useful information. So that is why we care about significant figures. Significant figures are the sorry, lost my train of thought. Are how we find significant figures is we start from the left side and ignore all leading zeros. So this one is just 3. So 3 meters, that's one significant figure. And then this one, we ignore those leading zeros. So this is also just 3. It's also just one significant figure. But then down here, if instead we had something more precise, like 3.0 meters, this 0 is not a leading 0, it's a trailing 0. So that one we assume to be more precise and also becomes one of our significant figures. So we have 2 here. And then the same thing with this one. Even after the decimal place, this one still counts as a significant figure. But important point with significant figures is you should not include more significant figures than you input. So, for example, if you're multiplying 3.5 and 1.5, both of these, if you just count, 2 significant figures, 2 significant figures. Now, if you plug this into a calculator, it will give you 5.25. That's 3 significant figures, but your inputs each only had 2 significant figures. So you need to round so that your output isn't more precise than what you input. So we should round this to 5.3 instead to make it only 2 significant figures. So that is this example here. Well, actually, sorry, that example, both of those had the same amount of significant figures. Now, instead, if we have numbers with 2 different sets of significant figures, here we have 2, here we have 4. Our final answer should not have more significant figures than the least precise input. So 3.5 is least precise because it has fewest significant figures. So that means we need to, sorry, losing my train of thought again. Round, there we go. Our answer down to 2 significant figures because that is the precision of our least precise input. So that means we go from 5.3759 to 5.4 in order to match our significant figures and not claim more precision than we actually have. So I personally am definitely not a stickler on significant figures. But this is kind of when people ask, this is the sort of baseline I would prefer you to think about is don't give me numbers like this. I don't think most of our numbers, I don't think we can be this precise most of the time. And try to be consistent, where your final answer shouldn't be more precise than what you put in. Because if what you put in wasn't precise, then really your output isn't either, you're just claiming it to be. Anyway, so you can refer back to this if you need to. So I was saying precise and precision. But let me actually define accuracy and precision. So accuracy is how close your measurement is to the correct value, and precision is how well repeated measurements agree with each other. So in this first example here, we have these points scattered all over the board. That's low accuracy and low precision. In this one, all of our points are really close together, but they're really far from the target, which is the middle. So low accuracy, but high precision. In this case, the points are all around the middle, the target, but they're pretty spread out. They're not super consistent with each other. So we have high accuracy because we're close to what it's supposed to be, and low precision because they're not really close to each other. And then high accuracy and high precision, all of our points are at the target and really close to each other. So when it comes to big or small numbers, we will be using scientific notation, and that looks like this. You figure out where you want to move the decimal place and count how far that is. So for this first one, we're moving the decimal place to between 6 and 3. And then we just count 1, 2, 3, 4, 5, 6. And that tells us, okay, our number with our new decimal place times 10 to the 6. And then we can do the same thing with something that is less than 0. If we want to move our decimal place between 7 and 5, again, this is 6, but we're moving in the opposite direction. So we're moving it backward instead of forward. And that means it's going to be negative. So 10 to the negative 6. Part of why I wanted to quickly mention scientific notation is because I also wanted to mention common metric prefixes. So we'll be using the metric system. I think maybe you had that idea from the fact that I talked about meters on the first slide. But here are some of the common prefixes and the values they relate to. So let's use meters as our base here. A gigameter is 10 to the 9 meters. A megameter is 10 to the 6 meters. A kilometer is 10 to the 3 meters. A centimeter is 10 to the negative 2 meters. And a millimeter is 10 to the negative 3 meters. And here's just a combination of standard units and common prefixes, just so you know what it will look like. So 1 millisecond, that's going to be written ms. And that's 10 to the negative 3 seconds, which would be given as s. Kilogram, and actually kilograms are what we're going to use, not gram. But kilogram is given as kg, and that's 10 to the 3 grams, which is g. And then a centimeter, which is cm, which I'm sure you've seen before, is 10 to the negative 2 meters, which is just m. So another thing with this is if we have specific typical physics units, then we're probably going to need to convert units when they aren't our typical physics units. For example, this example is given in miles. Miles is not a typical physics unit, so we need to convert it into meters or kilometers. We're going to go with kilometers this time. And in order to do this, sorry, 1 second. We want to look at the relationship between these two things. So how many kilometers in 1 mile, for example. So we figure out that factor, and you could just Google that. You don't have to have that in your head. I want you to know how to do the conversion, though. You shouldn't have, like, if you're going to do enough conversions in physics that it's not efficient to look them all up. But you can look up the conversion factors. Anyway, back to this. So the way you set it up, we know how many kilometers are in a mile. We looked it up. And then we want to figure out, okay, if I'm supposed to like somehow multiply by that conversion factor, how do I do that? Well, you set it up so that you can cancel out the units you don't want. So we have 60 miles. We want to get rid of miles. So we should put it on the bottom so that our miles units can cancel out. So we have 60 miles times 1.609 kilometers over 1 mile, canceling out the miles, gives us 96.54 kilometers. But we just learned about significant figures, and this number is more precise than what we put in. So we need to round to 97 kilometers. So I'm going to walk you through this last conversion here. But if you can pause and work on the other three, and it's just converting 14 kilometers into meters, 10 milliseconds into seconds, and 6 feet into a meter. And I gave you the conversion factor there, so you don't have to look it up. But anyway, I will do the 60 kilometers per hour into meters per second for you. 1 second. Okay. So we are converting 60 kilometers per hour into meters per second. So let's start by canceling out kilometers. 1 kilometer, actually, I'll just write these on the side. So 1 kilometer is 10 to the 3 meters. 10 to the 3 meters. So we'll put that here, 60 kilometers per hour. And so how do we want to set this up? Kilometers on the top, so that means that in our conversion factor, it should be on the bottom. So 1 kilometer here and 10 to the 3 meters up there. Perfect. That will cancel out kilometers. Awesome. Now we have hours. And for this one, we want to go from hours to seconds. And to do that, we need to go from hours to minutes and then minutes to seconds. So 1 hour is 60 minutes. And 1 minute, oh, no, those aren't together. Those are separate things, equals 60 seconds. So we're going to use that information. This time, the unit we want to cancel out is on the bottom. So we need to put it on the top in our conversion factor. So 1 hour divided by 60 minutes. And that will cancel out hours. And that leaves us, now we have meters per minute, but we want meters per second. So last one, we want to cancel out minutes, which are on the bottom. So minutes should be on the top, and 60 seconds. And that cancels out minutes, leaving us with meters per second, which is what we want. And then we can just plug our numbers into the calculator, and we get 16.67. Oh, not times anything. Meters per second. And we should round this. We only had 2 sig figs originally, so we should round this to 17 meters per second. Okay, so that is one of the examples. The other ones you have are simpler than this, and we will practice this more. Back to the slides. Okay, we're going to use a lot of trig in physics, and it's mainly what you see on this slide. We'll also use inverse tangent sometimes to find angles. But so we have this triangle here, and we know this angle up here in the corner, theta. And if we know this angle, we can define the sides based on it. So the side across from it is the opposite it. And the side that's next to it is adjacent. And then the long side is the hypotenuse. And just as a reminder, sine of the angle is the opposite divided by the hypotenuse. Cosine is adjacent divided by the hypotenuse. And tangent is opposite divided by adjacent. And then we have Pythagorean theorem. I didn't write it in the a squared plus b squared equals c squared way. I matched it up to how we labeled our sides. So hypotenuse squared equals the adjacent squared plus the opposite squared. And what we'll usually do is we're often solving for the hypotenuse. And so that's what I did here. I just square rooted both sides. So we have hypotenuse equals the square root of the adjacent squared plus the opposite squared. Now, so that was mainly math. But let's talk some real physics topics now. First off, position, where an object is in space. We know, we need to know three things to define the position of an object. A reference point to measure the distance from. We refer to this as the origin. The distance from the reference point to the object, from the origin to the object. And then which side of the origin the object is on. We treat positive positions to be to the right of the origin and negative positions to the left. In this example where we have cardinal directions, positive would be to the east and negative would be to the west. And that's just kind of the baseline we use in physics. So in this example, the post office is the origin and your car is 4 miles east of the origin, making your position 4 miles. This just the origin, or sorry, the post office is still the origin, but now we have a cow, and the cow is to the left or west of the post office, and it is 5 miles west, and that makes the cow's position negative 5 miles. And again, the negative is just because to the right of the origin is positive and to the left is negative. For horizontal motion, we use x as the variable of position. For example, in this snapshot, we have a runner and their position is 20 meters. And so x being their position is 20 meters, or x equals 20 meters. For vertical motion, we'll use y instead of x. So for this one, the origin is set at the ground, which makes sense. And then the numbers go up from there. And so we have this rock that's just right around 2 feet from the ground, from the origin. And this would be positive. And then if motion is on a linear slope, for example, we will usually just define x as along the slope. So where this here started is the origin. And the kind of x-axis just follows along the path that they're going on. So right now they are 10 meters from their origin. And it's positive 10 meters because it's to the right of the origin. So, but objects aren't always still. Sometimes they change position, and we call change in position the displacement. Here, Sam starts at this position 50 feet from the origin, which is this cross street here. And then he moves to a position 150 feet from the origin. And we want to determine what his displacement was. And we find that by subtracting his initial position from his final position. So displacement is given by this label here. So it's this delta, which you can think of as change in. So change in x, or the displacement, is the final position. So his final position is 150 feet. So 150 feet minus the initial position, which is 50 feet. So 150 feet minus 50 feet gives us a displacement of 100 feet. So looking at this, you probably, or there's a good chance you just did that in your head, but it's not always going to be super simple to do in your head. So knowing the actual equation relationship here is also important. And because signs, as in direction of things, matter in physics, what if instead Sam went to the origin? So his initial position was still 50 feet, but this time his final position is 0 feet. And if we plug those in, we have the final position, 0 feet, minus the initial position, 50 feet, giving us a displacement of negative 50 feet. So this negative sign here is important because it tells us that he went to the left instead of to the right. And this is why it is important to remember this relationship, because yeah, you can get that 50 is the size of his change in position, but it's not telling you the direction. And the direction's important. Speaking of vectors, we're going to be using vectors a lot because a lot of quantities in physics have both a magnitude and a direction, which is described by a vector. So the length of the vector shows the magnitude of the quantity, how big it is. And then the direction tells you the direction. That one's in the name. So this is how we're going to work to understand vectors. We have our vector here in red, and vectors are labeled with this arrow on top of them. So our vector A here in red, and then we also know the angle that A is from the x-axis, and that's angle theta. From the positive x-axis. And we can break our vector into its x and y components using trig. So we have the x and y components here, but because we know in this situation, we know what the hypotenuse is, our main vector, and we know what the angle is, we can use that to find the x and y components. And excuse me, that's what these are. So we start with, for example, just the cosine of the angle is the adjacent divided by the hypotenuse. So that's the x component because it's the one touching the angle, and the hypotenuse is A. And so all we did here to solve for A, the x component of A, is just multiply the vector A on both sides. That's all. I included this just so it's clear. I didn't want this to be like a magical equation that I got somewhere. No, it's just rearranging this equation. And we'll use this a lot. Maybe we'll have the vector value and angle, and we'll want a component. And so that's how we'll do it. And so the same thing with sine, it's just that it's the opposite over the hypotenuse is sine, and again, just multiplied that A on both sides, giving us the y component of it. And then there's also the Pythagorean theorem relationship. And we can also relate these sides by tangent of the angle between them. So for example, if we had the sides, the x and y components, but we didn't have the angle, we could use this equation to find the angle. And you take inverse tangent, that leaves us the angle equals inverse tangent of this fraction. And then down here, we have a way of representing the vector as like an equation with its components. And so we have x, and then we have this thing called I hat plus the y component times this thing called j hat. And let's take a look at I hat and j hat really quick. They are unit vectors, unit meaning one. So they don't change the magnitude of the value. They really are just there to tell us the direction so that we can list a vector in that equation form and keep the different components separate from each other. So this is just telling us that the y component is in the y direction, or you could call it the j hat direction, and the x component is in the x direction or the I hat direction. So now, yeah, let's say we have these two vectors, A and B, and we have this equation where vector A plus vector B equals this other mystery vector S. We want to use vector addition to find out what S is. And I'm just going to skip us to the next slide because I feel like it shows it easier. This uses A and B, but what you do, so you have vectors A and B. Vectors are described as the tail being like this end and the tip being the arrow end. So like they kind of start at the tail and end at the tip. So if we are looking for something where we're adding vector B to vector A, we start by just drawing vector A. And then we put the tail of vector B at the tip of vector A and draw it out. And then we go from the tail of vector A to the tip of vector B. And that gives us the sum of the two vectors. And you can see we made a triangle in doing that. You can also do this using numerically using unit vectors, the I hat and J hat representation. And this is bringing us back to that S vector as with A plus B. So if the A vector is the X component of A I hat plus the Y component of A J hat, and then B, same thing, but with B, what we can get is the X component of their overall vector S and the Y component just by adding the X components of A and B and adding the Y components of A and B. So if you have the kind of unit vector form of your two vectors, you can also get the unit vector form of their combined vector. And one more way you can look at this is kind of combining both of these ideas where we have the X component. So we drew these out like we were adding B to A. So we drew vector A, drew vector B from the tip of vector A, and then we drew our vector sum from the tail of vector A to the tip of vector B. But we can also, in doing that, look at the component. So we see, okay, here is the X component of A, this line here. And then B, we have the X component of B. It goes in the opposite direction. And we can do the same thing with Y. We have the Y component of A and the Y component of B. So these two combined, they're in the same direction. So the Y component of S is just those two combined. But in X, because the B component is in the opposite direction of the X component, they're subtracting from each other. And that makes the X component of our overall vector smaller. So that's what this is. So that was just really showing you the process of vector addition in like 3 different ways of doing it. We will mainly, well, no, we'll practice all the ways, I think. Now, vector subtraction works exactly the same as vector addition, but you just have a negative of the thing you're subtracting. So if we're looking for vector D and it is equal to A minus B, then we draw vector A. And then instead of drawing vector B here, like so instead of drawing it up like that, we draw negative B, so down. And then we go from the tail of A to the tip of negative B to get the resulting subtracted vector. And you can multiply a vector by a scalar, and a scalar is just a number, like a magnitude. It doesn't have direction. But if you multiply by a scalar, it will change the magnitude, not the direction. But if it's a negative scalar, it will change the direction. So we have vector A, and we multiply by 1.4, so that's just like a bit bigger. But if we multiply by negative 0.5, it's half as big, but also in the opposite direction. And that is the lecture. So you have a post-lecture assignment after this where you will practice some of these ideas, and we will practice them even more in class on Thursday. Hope you have a great day.